Good day, folks. This is tutorial number 41 in a playlist that is called Dynamic Scenario and Animation Modeling with 3D Experience. Let me remind you that the CATIA V5 program had a workbench in it, which was called DMU Kinematics. Now, that could only do the kinematics calculation, but in the new version of the CATIA, or the version of CATIA that's buried inside the 3D experience, there is also a dynamics, rigid body dynamics module that's buried. And that's why we can do problems like that in the 3D experience and not in the CATIA V5 program. Uh, it's not a complicated problem, but let me explain to you what is it that we're doing here. We have a plate, relatively thin plate, that is attached to this uh, base on the top, green base on the top, and there's a revolute here, and the plates start turning about that revolute base. The motivation behind this is actually coming from a second-year dynamics textbook by Miriam and Craig, and you can find it in most dynamics textbooks. So we have a plate like that that is being accelerated uh, at this rate, starting from rest. What we're asked to do is to find the initial needed moment about y and moment about the z-axis, which actually causes that acceleration, that angular acceleration. Now, this can be solved using usually the very last chapter in the textbook, which is three-dimensional 3D dynamics. And usually 3D dynamics and those chapters are skipped in second-year courses and are delayed to a graduate course or maybe an intermediate course or advanced undergraduate course in dynamics. But basically, you have to solve the Newton-Euler's equation, Euler's equation. And if you do that, for this particular problem, you come up with a moment about the z-axis, being given by that expression, and moment about y-axis is given by this expression here. Incidentally, if this plate is rotating about that pivot point at a constant angular speed, these are both zero, and the only moment that's going to be coming into a calculation or into the problem is going to be mx. But that's not what we're doing, okay? Anyway, in order to model this thing, what I'm going to do is I'm going to give it angular acceleration of 5 rad per second square, and dimension square, slanted square, 0.2 meter, angle 45 degrees, and assuming a mass of 1,000 kilogram with this plate. Now, if you plug these things into that expression on the top, you're going to come up with mz equal to 50 Newton meter and my equal to 33.3. Based on hand calculation, which is up here. Now, keep in mind that this 1,000 kilogram is kind of unrealistic for the dimension that I have, but that's really not the point of this exercise. Now, so basically, we really have two parts here. There is there is the base, call it the base, that green piece on the top, which is fixed, stationary, and there is a plate which looks like that, and eventually there is a revolute between these two, which make that thing turn. I'm going to assume that the dimension of the thickness is 2 millimeter, but that is not really important. However, I use 2 millimeters. And this is the way the end is going to look like. Now, what I'm going to do after I finish this, I'm going to come back and show you what happens if you decide to change a different angle, for example, 90 degrees. Yes, the same thing applies, except that you have to be very careful to just blindly go ahead and run the program for a different angle beta. And I'll come to this slide later on, but I put it up here for observation. And that's why I say be careful when interrogating the software. That deals with the last two slides, that if you blindly go ahead and run it without checking the stuff on the screen, you may get wrong answers. Okay. All right, let's go ahead and do that. Okay, so I'm going to start with the assembly design. Insert my first part, insert 3D part. I'm going to call this thing the plate. And plate here. Change the color to orange. Let's go make it. So double click on this. So on the YZ plane, I will sketch. I'll sketch a rectangle, a slanted rectangle. This is the way I prefer to do it, but it's entirely up to you. So I have a situation like this. Yep. Let me dimension these things. So dimension this to be 200 millimeters. And the thickness of this plate, I decided to choose 2. It's entirely arbitrary, but I'll choose 2. All right, and then I make sure this is 45 degrees. Suspension is 45 degrees. So dimension between this line and that line, 45. Excellent. So exit. There we are. And then we pad it symmetrically in each direction by 100 millimeters. There we are. So this is going to be almost my plate. Now notice that because I can hardly see these directions, just to make my job easier, I'm going to put an axis system there so I can see it. So here is, look, axis system automatically puts it there. So Y this way, Z up, and X is along that. Okay. So I'll just leave it like this. Good. All right. Now, on that horizontal plane, I will draw a little circle because I want to make that stand where the Revolut is going to be created. So a little circle there. The actual dimension of it doesn't matter. But here, I'll make this thing maybe 1, radius 1. Okay, exit. I'm going to pad this thing up by 10. By 10. And if you want to be able to see the bottom of it like that, you might say, well, this cannot be a weld, etc. No problem. So I can actually, what I can do is, let me do this. Just a second. This pad. All right. So I'll make this thing bigger so it looks like it's going through that and attached to it. I mean, maybe that you may not like it because it's endpoint, no problem. Just make it 1 millimeter shorter, maybe 1.5. This is really unnecessary, but I did that. Okay, so that takes care of the plate. Very good. So, yep. Let's go all the way to the top, insert our second 3D part, insert new part, 3D part. I'm going to call this thing the pivot, or I'll call it the base. Okay, properties. Call it base. Okay, and the color of it, I'm going to make green. All right. So uh, on that plane, I will sketch. Oh, let me go to the part design actually. Part design. On that plane, I will sketch. right there. So I'll draw a circle, just a little bit tiny, a little bit bigger than that. I'll make it a little bit bigger. Exit and pat it in the other direction. Where is it? Where did it go? Reverse. That's too tall, so I'll make it maybe a 5mm preview. There we are. Okay, very good. Let me do a quick save here. File save. Now, we're going to create our joints. So obviously that green one is going to be fixed part. So let me go ahead here. Let me go ahead here with fixed, and it's the green one. The base is going to be fixed. Yeah, it's right here. Green one, base is fixed. And then we create a revolute between this and that. So we create a revolute. And there's a template that's going to open up. I'm going to use this one. It really makes no difference. I'll use this one. So here's the situation. Axis of this green piece, axis of the plate, shaft of plate. And let me see. I'll make this plane of the green piece and the top plane of the plate. And for controlling the angle, I'm going to do the vertical plane of the green piece. For example, let's say YZ plane, and the YZ plane of the plate. Right now the angle is 0. That's fine. This is how I'm going to control the motion. All right, good. Okay, so there we are. Let me update everything. So once our joints are created, we go to mechanical systems design. Why don't we go and apply material to this? Well, I say material, assign mass. Okay, so that's done. I can do that now, or I can do that after I create the mechanism. Let me go and create my mechanism. Mechanism representation right there. See, I'm in the mechanical system design, mechanism representation. Say okay. Look at what you've got. Click on the mechanism manager. You have a fixed part. You have revolute point. The revolute one is, of course, it's controlled by the angle. Remember those vertical planes at the end. Okay, good. Now, can I check it? Can I check it? Click on the mechanism player. Not a big deal. This is just kinematics. Okay. Reset. Say okay. Now we're going to assign properties, mass properties. So I go, when you're in mechanical system design, you go all the way to the right. It says weight definition. You click on it. Notice that you get 2 red colors. That means nothing is defined. So if I click, for example, on the plate, there's the plate. See that? Plate. Click on it. It says, click this hyperlink to declare a weight on this element. Click on it. Now, here's what happened. Because I don't have any material defined on it, if I check this box on the top left corner, see this? Right there. You click on it, default properties of steel are assigned to this. Now I can change it. I want the mass of this piece not to be that much. I want it to be 1,000 kilogram. Unrealistic, but that's okay. Now, look what happened, by the way. When I made it 1,000, all these numbers changed. Now, these numbers give you 3 moments of inertia and 3 products of inertia. These should check the theoretical calculation that I have here. If you go to your, I mean, there's my MathCAD sheet. It's like my spreadsheet. Beta is 45 degrees, M is 1,000, B is 0.2, and later on we're going to let alpha equal 5. That's the angular acceleration. But look at what happened. If you look at IZ, it's going to be minus, IZ is going to be 5 kilogram meter squared. Let's check that. 5 IZ 5 kilogram meter squared. Okay. Now you can also do these other two. It's going to be, of course, IZ and Y. You can check these two. That's okay. But it's the other one that I want to look at. It is YZ is minus 1.667. Minus 1.667. YZ. Minus 1.67. Now, just be careful because these things are with respect to the coordinate system that passes through the centroid of that. It's with respect to these guys. Okay, just be careful. But anyway, so far theory agrees with our hand calculation or with our 3D simulation. So far, these are okay. Now, let me close that. Once you're done, you just close it. Remember, I checked this, default properties of seed, and I changed that. As soon as I change that, these numbers change too. This stuff is going to be critical later on when I come to changing values and that last slide. We'll come back. Let me close this, and I'm going to close that. Excellent. Now, we defined properties. Now we have to specify the acceleration. So how do we do that? Well, first of all, in order to do this, we have to go to mechanical systems experience. I mean, there are 40 other tutorials on this topic, right? Say okay? Say okay? In this playlist, there are 40 other tutorials on this topic. All right. So what we're going to do, we're going to specify, and notice that if we know the angular acceleration, we know the position, angular position of the plate, basically 1/2 alpha t squared. All right, 1/2 alpha t squared. So angular position comes from this formula. Okay, so let's go here. Go to law excitation. Click on it. This thing pops up. It says, where is the support? The support is that revolute joint. The command of that revolute joint, right there. You can't select any of these. The command, it wants the command. And then you put a formula there. Click on f of x. It's going to be 0 plus. Doesn't matter. You can write, just take away that 0 degrees, but I leave it like that. So 1/2. So I'll write it as 0.5 times alpha, and alpha is 5 radians per second squared. You got to be careful about this thing when you write it. So let me write it as I can write it like that, times 5 rad underscore S2. We're going to check this. Okay, S2. Do I have to convert it degrees? Not if you wrote it like that. This is fine. Okay. Times squared star 2. Now the units must be if I say okay here, you may get a warning message about units not being consistent because my units are in degrees and this thing has rad in it. Let's check it out. No, it's okay. It took it. It took. We're going to check that. We're going to check that. Okay. Say okay. All right. Now let's go and create our. Let's go and create our uh, dynamic scenario. Click on this dynamic scenario. Okay. Click on that dynamic scenario. Here is my excitation, law excitation. Send that to the right. Parameter, let's do it over 2 seconds. Okay. All right. And I think we are good. We are good. So let's go ahead and run it. Right click. Later on, I'm going to come and add a joint to a probe to it later on. I'm going to run it. First of all, if I did everything correctly, that's okay. We'll take care of this thing later on. The angle must be 2 degrees, not 2 degrees. Let's see that. What is it that we've got here? After 2 seconds, the angle must be 573 degrees. If I don't have that thing, I'm going to go check my units again. So let's do a results. Show me the angle. Just deselect everything. Show me the angle. Must be 500 and something. In fact, if you look at the table, here is the angle, 572. 572. Okay, good, good. Now I did get that warning message that I didn't like, so let me go and run it again, and this time I'm going to read it to see what the issue may be. Let me try this thing again. Right click. Let me run it again. No inertia. Oh, you know what? I forgot to specify the mass of that base. Ooh, yeah. So let's go back. I forgot to do that. So we go to put the cursor there, right click, switch to mechanism, go all the way to the right. Notice that there's a red piece here, right there, which says that, hey, I'm stationary, but you better give me mass. So no problem. So I'm going to select the, what was it called? Base. Notice it's red. Assign link, the hyperlink, click on the hyperlink. Since it doesn't matter, I assign default properties of steel. I'm not going to change it. Just leave it the way it is. No problem. And then close. Okay, you're good. Let me close that. Go back to scenario and run it. It's not going to give me that error message anymore. Because it said you're doing dynamics calculation and you did not give me the mass of that stationary piece. Okay. And then of course we can always check again one more time. So if you look at, for example, deselect everything, look at angle, and the angle will be, it's going to be the same answer. Did I ask for it? Hang in there. This one. The table, 572. Okay, good. You're on the right track. Now the question was not this though. The question was something else. The actual question was, what is the moment about Z and the moment about Y in order to make this motion take place? Okay, no problem. How do I do that? So we go back to scenario right there, and notice that there is a probe here. There is a joint, you see that? Joint force probe right there, joint force probe. You click on it, and then for the joint, we're going to select the revolute joint right there. Or you can do the revolute joint, that's fine. And when you look at revolute joint, you can either look at the base or you can look at the plate, it doesn't matter. Oh, I'll look at the base and look at the options. You can have the joint frame XYZ or global frame XYZ. I'll use the global and I say okay. And now I'm going to run. 2 seconds, right? But I want the initial stuff. Okay, so go back here, click on this, click on that. Okay, now deselect everything. Give me these things. Let's check. Let's check these three first. These are the internal torque. So later on, I'm going to come and do the force probe right there. So if you look at the internal torque, I chose all of them, but it's not needed. Some of them are 0. So there is your Z. This Z, this Z is the match to that. Okay. Now, if I go, keep that in mind. Go back here, deselect all, come down to here, select these. This is from the probe. This thing, 38. Why? Is supposed to be that. Okay? Supposed to be that. So there's some obviously deviation. We can see that we don't dispute that. So this is the initial one that we want. Okay. So we know that we need Y torque and the other one. So I want this one and the Z over there. So these are going to give me what the initial value. Of course, as time goes on, these things will change. Not that one, but initial torque 38.8. So that is supposed to be matching. It's supposed to be compared with this. Now, just keep in mind that we don't expect to get identical values because this is really not the same exact geometry, because when you do analytical calculation or that you solve the Newton-Euler equation to get these things, you really don't have a situation like this. You assume that the plate is a plate without any, obstruction like that. Now, what is this all about? What do I mean? What is this all about? Suppose I decide to change that angle 45 degrees to 90 degrees, right there, 90 degrees. Okay, so let's go and do that. Let's go check. I go to that sketch for plate sketch right there. This was the plate sketch. Double click on it. This angle, 90. So it looks like that. Okay. Exit. So far, so good. All right. Everything is the same. Everything's the same. Suppose I go and run this thing. I go and run. Mass has not changed. No problem. And let's go and look at the same stuff that we looked at before, namely deselect all. This was Z, and this one was Y. Z, Y. Remember, it was 50 and it was 38 point something. Let me get the almost 50. These numbers did not change. These numbers did not change. So that is where this slide comes into the picture. It says, look, go and basically put that material in recycle bin, apply properties of steel, default properties of steel, and then change it. So let's try. Let me put this thing down. Let me go ahead to switch to mechanism. Go there. Click on that. You see, this is what I had before, and these are the numbers that I had before. It says, put this thing in the recycle. Just keep that in mind. This was, for example, 5, and this was minus 1.67. Just remember that. Let me go put that thing in recycle bin. Do it again. Apply properties of default properties of steel. And now I'm going to change this thing to 1,000. When I hit return, these numbers at the bottom should change. Okay? I'm going to hit change. Okay, so I'll change that. These things change. So, and notice that these two are 0. That's good. Close that. And now I'm going to run. And then we're going to look at those entities that you want. Click. You select all. Let's look at these things. So let me check all of them. Some of them are unnecessary. Okay, the table. Okay, so I want, there is your Z torque. So I want the Z internal torque and the Y torque, Z internal and Y. So let me go ahead here. Deselect all, Z internal and Y torque. Look at the values. Now, I don't particularly like the fact that these numbers, this column is not 0. This is okay. This is very close to what I have. Don't let the negative signs bother you, and I will let you know why later on. Now, my suspicion is that the reason that the Y torque is high, you're not getting what you expect. 0 is this thing is too long. So what I'm going to do is I'm going to go to this pad, and instead of 20 millimeter, I make it 1 millimeter. Okay. And then we go back here, update the system, and we're going to run it again. We're going to run it again. You know what? Just to be on the safe side, what I'm going to do also is I'm going to assign those. I don't think it's necessary. I can probably get that thing reduced, but just to be on the safe side, I'll go here, weight definition. Let me see now on the plate. I'm going to put this thing in recycle box bin, and then default properties, and I'm going to put 1,000 here. Once again, I don't think this was necessary, but just to be on the safe side, this is what I've done. All right, very good. So close it. All right, and we're going to run it. Notice that I eliminated that 20 millimeter pipe there. So let's run it. Okay, let me double click on this and now run it. And look at those two entities that we're looking at. So click on this, deselect everything. There was Z internal torque and a Y torque here. And look at the table right there. So these didn't change, but this got reduced from a value of 8 to value of 1, basically 1.5. And that is supposed to be 0. Now, the one thing is that about these negative signs, notice that, let me close that for a second. When you look at the internal joint probe, you have to specify some option. I decided to do the global frame and the global frame, but here I'm displaying this thing on the plate or on the base. If I say on the base, say okay and run it, all those negatives are going to be turning into positive. Well, for why? So let me see now. Yeah, I guess this one if you do the magnitude, obviously, it's going to be 83. So, but anyway, that didn't bother me. So this is fine. So the moral of the story is that you gotta be careful, because when you change the number here initially, things will change. But if you change it subsequently, uh, certain things may not change. And I don't like that, but that's what I've got. I've got to work with it. Good luck.